Okay, so in this lecture, we are going to discuss about group actions. Group actions. Clear? So let's straight away come to the definition of it. So let G be a group. Let G be a group and A be a non-empty set. Okay, and A be a non-empty set. The action of G on A, so it's a map. It's a map from G to A. So from G cross A to A. So it's a map from G cross A to A such that the ordered pair GA is mapped to a symbolically denoted as G of A, let's say. Okay. Conventionally, we also do not use specifically the operation. We can simply write it as somewhat of this form G. Okay. We will use this notation if there is no chance of being confused with the general group multiplication. Okay. Yeah. So this operation this operation needs to satisfy two important properties. Property number one. So G1 G2 on A is same as G1 on G2 on A. And number two is 1 acting on A is 8. So this happens for all G1 G2 in capital G and A in capital A, and this obviously happens for all A in capital. Okay, so the action of G is this map which satisfies these conditions. We denote the action on G as G acting on. Let me change the template. Okay, wait a minute. So let me take the rule paper only. Okay, yeah, correct. Okay, this will do. Okay, so we denote the action on G as G acting on. Yeah, correct. Okay. Okay. Now, notice one thing that suppose G acts on A. Okay. Suppose G acts on A. So what we do is we fix some element small g in capital G. Okay. Then we define a map from A to A, which we denote as sigma G. So sigma G is a map from A to A such that what does sigma G does is it maps an element A to G on A. Clear? So I guess this map is pretty evident to understand, right? So what we are actually doing is that, so we had a map from G cross A to A. We are just formally changing it to a map from A to A by fixing some element small g in capital G. Okay. Now notice that sigma G is a bijective mapping on A. The reason being that what is sigma G inverse of sigma G on A? So this is sigma G inverse G on A. So this is G inverse on G on A, but this can be written as G inverse G on A by the properties of group action. So this is nothing but A, right? Similarly, sigma G of sigma G inverse A, this is sigma G of sigma G inverse of A. This is nothing but G on G inverse on A. but this can be written as G inverse on A, and that is also. Therefore, an inverse mapping exists, right? So this is a bijective mapping. And if sigma G is a bijective mapping on A, so formally speaking, sigma G permutes the elements in A, right? So therefore, sigma G permutes the elements in A. The elements in A. If I consider an example, let's say suppose A is of this form. So let's say A is of this form 1, 2, 3, and 4. Okay. We consider a group G which acts on A such that some element G, we fix a small element G from G, then G composed with 1, suppose this is 2, G composed with 2, suppose this is 3, G composed with 3, suppose this is 4, and G composed with 4 is say, right, let's it's 1. Okay. Then notice that, so sigma G sends 1 to 2, similarly sigma G sends 2 to 3, sigma G sends 3 to 4, and sigma G sends 4 to 1. So what does this sigma G basically do? So sigma G just reorients the elements in A. So it sends 1 to 2, it sends 2 to 3, it sends 3 to 4, and it sends 4 to 1. So it just reorients the elements in A. But how is this in any way necessary? Because having defined such a sigma G and having the fact in hand that this sigma G is nothing but a permutation on A, therefore we can define a mapping phi from G to SA, where SA basically defines the set of all bijections of the elements in A, a set of all permutations of the elements in A, such that any element G is sent to sigma G. Clear? Now sigma, now this is necessarily a homomorphism, because if you consider phi of G1 G2, then this is nothing but sigma G1 G2, and sigma G1 G2 is nothing but so this is G1 G2 on A, so this is G1 on G2 on A, but this can be written as sigma G1 of sigma G2 of A, right? And so by the composition operation, this is obviously in multiplicative form, right? So this is of the form sigma G1 sigma G2, and this is nothing but phi G1 phi G2. Right? So this is a homomorphism. Therefore, if you have any group action, thus any group action has a permutation associated with it, right? Has a permutation associated with it. So this permutation is called as the, so this is called the associated permutation representation afforded by the action. Okay, it's called associated permutation representation afforded by the action of G on A. Clear? One more thing to observe here is that if you consider the set of all permutations from G to SA, okay, so you have a group G, you have a set A, then you form a collection of all possible actions of G on A, and you form the set of all possible mappings from G to SA. Then there's obviously a 1-1 correspondence between them, right? Why is it so? Because if you consider a certain certain mapping from G to SA, then you can obviously induce an action out of that very mapping by simply following the steps backward. as we formed the associated permutation representation, right? So that means with respect to any mapping present here, you can form an action, and the converse is also constructed. So therefore, there is a 1-1 correspondence between the actions of G on A and the mappings from G to S. Rather, I should say the homomorphisms from G to S. So this is the set of all homomorphisms from G to S. Correct. Got it? Let us go through a few examples to have a more grip on the concept of group action. So the first example is, so let G act on A by G on A giving you A itself. Okay. Obviously, G is a group and A is an arbitrary set. I won't mention that every time. So this is called the trivial. This action is called the trivial action. The trivial action of G on A. Clear? Obviously, what should be the associated permutation representation? So associated permutation representation, we will use the shorthand notation APR. So the associated permutation representation is nothing but the identity mapping from G to S, right? So basically, so associated permutation representation is the homomorphism from G to SA such that G is mapped to the identity. G is mapped to the identity. Clear? What is the identity on S? It maps every element in A to itself. Right. Let's take the next example. Example 2. Okay. Okay. Now there's a definition associated with example 2 is that let G be acting on a set A. Suppose distinct elements in G induce distinct permutations in A. The other way of saying this is the associative permutation representation is injective. Okay, that is the APR is injective. Then the action is said to be faithful. Then the action G on A is said to be faithful. Is said to be faithful. Clear? Okay. Number 3. Let G be acting on A. Then we define the kernel of the action. We define the kernel of the action as the set of all the elements G in capital G such that G of A is nothing but, and this happens for all A in capital. Okay. Notice two things from here. First thing is, if you consider the associated permutation representation of the action, this, and let that associated permutation representation be sigma G, then what is kernel of sigma G? What is kernel of sigma G? So kernel of sigma G is basically, so kernel of a homomorphism, right? So kernel of sigma G is basically the set of all the elements G in capital G such that sigma G is identity, right? Sigma G is identity. So what does sigma G in identity mean actually? So this means, so it's the collection of all the elements G in G such that G of A is equal to A for all A in A. right? And that is same as the kernel of the action. Clear? Clear? So one more thing to notice from here is that we had said that that any action is said to be faithful if the associated permutation representation is injective. So we can also say that so if we just check the kernel of the action and the kernel of action is coming out to be identity, then obviously we can say that the uh, the action is faithful, and the kernel of the action is identity. That basically means that only the identity element from G fixes every element in A, right? Okay. This this type of a mapping or this type of an operation is called fixing the element A. Clear? Suppose G acts on A trivial. G acts on A trivial. Then we know that G on A is nothing but A. Therefore, kernel of the action is whole of G. Right? Thus, if the cardinality of G is 1, then the cardinality of the kernel of the action is also 1. But that means kernel of action contains only the identity. Right? That means the action is faithful. Right? So if we have a trivial action by a group of cardinality 1, then the action is faithful. If the action is obviously trivial. Clear? Okay. Let's come to the next example. Okay. So let A be a non-empty set and consider the group of all permutations SA. Then SA acts on A by an element from SA on A is nothing but sigma of A. And this is pretty easy to understand, right? So basically what we are doing is, by considering an example of this, I mean a deep analysis of this. So suppose SA basically contains all arrangements of the elements in A, and A is the collection of those elements, right? A contains the elements. So SA acting on A actually works as a, it works as a tool. So as the elements in SA, they work as a tool which permutes the elements of A. You can think of SA as a machine. When A is implemented in the machine, the outcome is different rearrangements of it. Clear? Okay. The next example is a bit important and also a bit complex, but you can obviously understand it. So consider an n-gon. Consider a regular n-gon. Consider a regular n-sided polygon, that is. Clear? Then obviously each element of D2n, or you can also write it as Dn itself, permutes the vertices of the n-gon, right? Therefore, now what is D2n? So D2n is basically set of all possible symmetries of a regular n-gon, right? So therefore each element in Dn gives rise to a permutation of the vertices of the regular n-gon, right? what we are actually trying to do is that we can think of it like, let's say, let's consider an example. So suppose we consider the regular trigon as a triangle. It's an equilateral triangle. So we index the vertices as 1, 2, and 3. Clear? Now consider the element S from. So what is actually D3 looks like? So it's the element 1 3 sorry 1 R R square S S R S R square, right? Where S represents reflections and R represents rotations. What are the possible rotations? Obviously, so we can rotate 1 to 2, 2 goes to 3, and 3 goes to 1. This is one possible rotation. Right. What is one more? So one is the triangle itself. It is not rotated, which is the identity element. Next, we can rotate 1 to 2, 2 to 3, and 3 to 1. Also, we can rotate. Let's say we can rotate 1 to 3, 3 to 2, and 2 to 1. Yeah. So these are the three possible rotations. And what are the reflections possible? So we can just have a line from in between. So 3 can be interchanged with 2. This gives you one rotation, right? If you do this, then 1 interchanged with 2 is another rotation, and 1 interchanged with 3 is another reflection. 1 interchanged with 3 is another reflection. So these are the three possible reflections. Clear? Clear? Now if you choose an element from D3, okay, let's say you choose the element R square from D3. So formally speaking, what does R square actually do? So it's two corresponding, so it actually replaces the vertices twice with its corresponding vertex, right? So 1 goes to 2 is one rotation, and then 2 goes to 3 is another rotation. So this is induced by R, then this is induced by R, so this is induced by R squared, right? This is what I actually mean to say. So therefore, if you consider the elements, the vertices as the elements 1, 2, 3, then what is R square of 1? So R square of 1 is actually, after rotation twice by 60 degrees, where does 1 reach? So 1 goes to 3, right? So 1 goes to 3. Similarly, R square 2 goes, 2 goes to 1, and 3 goes to 2. So therefore, R square is a permutation. So R square is this permutation, right? So 1 goes to 3, 3 goes to 2, and 2 comes back to 1. So it is this very permutation. Clear? That is actually what I meant to say. Got it? And so this is the basic reason why we often say that D3 is isomorphic to S6. Because every element of D3 gives rise to some permutation of the elements 1, 2, 3 when we have indexed the vertices as 1, 2, 3. And D3 has exactly 6 elements, right? So every element should cover every possible permutation of the numbers 1, 2, and 3. Clear? Okay. Let us consider the next example. And today's lecture will be completely dedicated to this example only. Okay. So, yeah. Okay. So number 5, I see. Yeah, it's here. So let G be acting on itself. Okay. So a group is acting on a group itself by, so G on A is nothing but the normal group multiplication. So it's the group multiplication. That is the group. The group is obviously chosen to be a multiplicative group, and so this is simply the group operation itself. So basically speaking, so I'm writing it here, if G is additive, then we define G on A as G plus A. That's it. Clear? Clear? So this is called the left regular action of G on itself. Okay, so this is called, this action This action is called the left regular action of G on itself. Clear? Now this action is obviously faithful, right? Now why is it so? Because suppose you have sigma G1 equals to sigma G2, where sigma G is basically the associated permutation representation with respect to the element small g in capital G. So if this is equals to this, then this is nothing but G1 of A to be equal to, so G1 of A to be equal to G2 of A. But that is equals to G1A equal to G2A, right? By the definition of the group action. But left cancellation holds in, sorry, right cancellation holds in G, right? Because G is a group. So we can obviously right multiply with A inverse to get G1 equals to G2. So that implies sigma is 1, 1. Therefore, the left regular action of G on itself is faithful. Is faithful. Clear? Now we come to some important terminologies related to group actions. Okay. Definition. Let G act on A. Let small a, or rather I should say, I should define this. For all A in A, we define the stabilizer of A. We define the stabilizer of A denoted as GA as, so it's the set of all the elements small g in capital G. Wait a minute. So this is the set of all the elements small g in capital G such that G on A is A. So basically stabilizer is the set of all the elements in the group which is acting on the set A, which fix A, which fix every element A in capital. Clear? Got it. Now one thing to be noticed here is that, so what is kernel of this action? So kernel of this is basically G in G such that G on A is A, and this happens for all A. So this happens for all A. That means kernel is the set of all those elements in G which fix every element A, right? So this can be written as the intersection of all the elements in G which fix some A in A, right? And the intersection taken over capital, right? So this is intersection of all the GAs, right? Clear? So GA, that is the stabilizer of A. So I have written it wrong. Stabilizer of small a in A. Yeah, correct. Sorry, small a in G. Stabilizer is small a in G because stabilizer is obviously a subset of G. It is indeed a subgroup of G. Okay. Whatever be it. So the kernel can be defined as the intersection of all the stabilizers of all the elements in A. Clear? Got it? Okay. Now, if G acts on A and sigma small g is the associated permutation representation afforded by this action, then we know that kernel of sigma g, so this is a normal subgroup of G, right? I guess we had studied in the first general group discussion that the kernel of a homomorphism is subgroup of G, or might be in the second one. I don't exactly remember, but I guess we had studied it. Okay. If not, this is pretty, this is very simple to check, because let me just, give a brief fact about it. If you consider any element from G sigma G inverse, or I should, so let me be general in this. So suppose phi from G to H is a homomorphism. Suppose this is a homomorphism. Okay. Then if you consider the elements, let's say G K G inverse, such that K is in kernel of phi, then what is phi of G K G? So phi of G K G inverse is phi G, phi K, phi inverse, phi G inverse. But phi of K is 1, right? Because K is from the kernel. So this is simply phi G inverse. But that is equal to phi G of G inverse, which is equals to phi 1, and that is equal to 1. Right? So what does this mean? So this means GKG inverse. So this means GKG inverse is in K, where K is the kernel of phi. Okay. But since small k is chosen arbitrarily from K, so that implies G capital K G inverse is a subset of K. And the other side inclusion is trivial. Therefore, G K G inverse is equal to K, and thus the kernel of a homomorphism is always a normal subgroup of the domain group. Clear? So kernel of sigma G is normal in G. Right? Therefore, we can obviously consider the quotient group. This, right? Right? We can consider this. Thus, now, okay. First, now notice. Now see, one thing is that if you consider any two group elements and they induce the same permutation on it, okay, any two group elements, so they induce the same permutation on it, then what does that mean? So that is if and only if the two group elements are in the same coset, they are in the same coset of kernel of the action in G, or kernel of sigma G in G, where sigma G is the associated permutation representation. So therefore, any action G on A can be viewed as a faithful action of the element of the group G mod kernel of the action on A. Or let me be a bit more precise. We can think of it as the action of G mod kernel of sigma G on A, where sigma G is the associated permutation. Clear? Got it? One second. Okay. Yeah, so so we have understood what a stabilizer of an action is basically defined as. Okay. Next, what we do is that, let me go to the next page. Okay. So okay, one more thing to notice from here is whatever we were speaking about is that if A is finite, and G acts on A, suppose, okay, let me write it like this. suppose the number of elements in A is n and G acts on A, then obviously SA is isomorphic to Sn, right? The all possible permutations of the elements in A is nothing but isomorphic to all possible permutations of the elements 1 to n. So that means, therefore, the associated permutation representation of the action G on A is equivalent to phi from G to Sn, right? Where phi is a homomorphism. Therefore, in case of a finite set, if G acts on A, then we can obviously induce an homomorphism from the group G to the symmetric group Sn. Clear? Now, let G be acting on A. Okay? Define a relation, say this, on A by, so we say A is related to B if and only if A is equals to G on B. Clear? For some G in G. For some G in G. Then this is an equivalence relation. This is an equivalence relation. Now you can always consider this an exercise to prove. So let this be an exercise. This is very easy to prove. Okay, so this is an equivalence relation. And so, since this is an equivalence relation, therefore we can form equivalence classes, right? So we define, so let's say the equivalence class of A to be this. So this is the equivalence class of A. Then we say that the equivalence class of A is nothing but the index of the stabilizer of A on G, okay, which is the index of the stabilizer of A. Now this proposition can also be viewed with respect to any equivalence class containing A, right? Because we know an important property of an equivalence class that either they are disjoint or they are the same. So if A is inside any certain equivalence class, then that equivalence class has a non-empty intersection with the equivalence class of A, hence they are the same. Okay, so proof. Define a bijection between the left cosets of GA in G and the elements of the equivalence class containing Clear? We define, let C of A be the class of A, that is the equivalence class of A. So basically C of A is nothing but the set of elements G of A such that small g is in capital G. Right. Now suppose B is equals to G of A. So this is obviously in the class of A. Then G of capital GA is a left coset of GA in G. So what is the map we choose? So we basically map B, which is equals to G on A, to the left coset G of GG capital. Okay. So this is obviously a mapping from CA to the set of left cosets of GA in G. And this mapping is indeed surjective by definition and clearly injective, right? Because if why it is clearly injective? So if G of A is equals to H of A, so this can happen only if and only if H inverse G is in GA, and this can happen only if G of GA is equals to HGA, right? So it's obviously injective. Clear? And it is surjective by definition, therefore is a clear-cut bijection, right? Clear? So if it's a bijection, then what are the number of elements in the class of A? The number of elements in the class of A is nothing but this number of elements in the left cosets of G, in the set of all left cosets of GA in G. That is only the index of GA in G, right? So that is the end of the proof. Clear? Now these equivalence classes with respect to this very equivalence operation, equivalence relation, is called the orbit of the element. Okay. The equivalence class of A is defined as the orbit of A. Clear? Defined as the orbit of A. So if you choose an element small a in capital A, then the orbit of A, let us define as OA. See, the orbit of A is defined as the elements of the form G of A for all G in G. Or we don't even require this for all G in G, so that G is in G. This will do. Right? Clear? Okay. So this is called the orbit of A, right? So the next definition is that an action G on A is said to be transitive. Is said to be transitive if there exists only one orbit of A. Only one orbit. That is, for all AB in capital A, there exists a G in G such that every B can be written as G of A. That is the other way of saying. So what does this mean? So this means that A is equivalent to B with respect to the equivalence relation which we have defined for all ABs. That implies G has only one equivalence class. G has only one equivalence class. So that implies G has only one orbit. Clear? Okay. Now let us consider an example of this and we end this lecture. In the next lecture, we will be starting with the some certain specific important types of group actions. And the first we will be considering is the group action on itself by left multiplication. Okay. So let's consider a few examples. Let's say example number 1. So if G acts on a set A trivially, then notice that the action is transitive if and only if this is 1. This comes direct from the definition of being transitive and trivial action. Okay. Clear? Number 2, let's say. Okay. Suppose, okay, we can say that D4 acts trivially on a graph this where the graph is consisting of the vertex set V and the edge set E, where the vertex set is indexed with elements 1, 2, 3, 4, and the edge set it is consisting of the edges, the corresponding edges. So it's 1, 2, 1 second. Yeah, so it's consisting of the elements of the edges 1, 2, 2, 3. So it's 1, 2, 1, 2 is an edge, 2, 3 is an edge, 3, 4 is an edge, and 4, 1 is an edge. So we can consider this in the form of a square, let's say. Okay. So we have 1, 2, 3, and 4. Clear? Clear? Now D4 acts, sorry, not trivially, D4 acts transitively. D4 acts transitively on the graph. This. Every element will be related to every other element. Clear? So there will exist only one orbit. Okay. What will be the stabilizer of any vertex? So notice that stabilizer. So let me consider this as an exercise. Just analyze this very example. So the stabilizer of any vertex is the subgroup of order 2 generated by the reflection about the line of symmetry passing through that point, about the line of symmetry passing through that point, Clear? Okay. So let this lecture be up to this much. In the next lecture we will be analyzing the concept of group action on itself by left multiplication. So meet you guys in the next lecture.